Today, we're going to be talking about minerals. And if you're following along in the Marshak book, this is chapter 3. If you're following on the online book, the Earl book, it's chapter 2. Okay, so what is a mineral? A mineral is naturally occurring solid formed by geologic processes that has a crystalline structure and definable chemical composition. And almost all minerals are considered inorganic. So let's figure out what that means. There's this really great YouTube video that does a really good job of explaining minerals in a nutshell. And I'm going to show you that YouTube video, and then we're going to jump back and reiterate basically some of the same material that is addressed there.
Hi everyone. In this video, we're going to be talking about minerals. So let's get started. What are minerals anyway? Well, in the simplest sense of the term, minerals are the building blocks of rocks. Here's a rock. This is a piece of the igneous rock called granite. If you look carefully at this chunk of granite, you'll see all sorts of speckles of gray and white and black. And if you zoom in, you'll see that these are actually crystals, mineral crystals. This particular piece of granite has the mineral quartz, biotite mica, and plagioclase feldspar. We'll study these in more detail later on. So, on Earth, there are over 2,000 varieties of minerals, some of which are seen here. As you can tell, they come in a wide variety of colors, shapes, sizes, textures, and all sorts of different physical characteristics. Minerals have quite a few uses in our everyday life. Just to give you an example, this here is a rough, uncut diamond. Of course, we use diamonds for jewelry. We also use diamonds in construction applications, as the tips of saw blades, and a variety of other industrial uses. Here's another mineral. This is called fluorite, most famous for its inclusion in toothpaste. Yes, when you see the name fluoride on a toothpaste, that means it's made out of the mineral fluorite. But what else are minerals used for? Well, this here is talc. Talc is a very common mineral that is ground into a fine powder. It's very soft, and it's used in baby powder. Sometimes you might hear it referred to as talcum powder. One more example. This is a mineral selenite gypsum, which is used all around us in drywall. This is the material that's used to build the walls inside modern houses and buildings. But what exactly makes a mineral a mineral? Well, to be considered a mineral, the substance must meet 5 criteria. Let's go through those 5 criteria right now. Number 1, the substance must exist as a solid under normal conditions on Earth. This means if you have a liquid or a gas under normal conditions, it cannot be considered a mineral. It must be in the solid state. Number 2, the substance must be naturally occurring on Earth. This means it cannot be man-made. So, for example, plastic is not considered a mineral because it doesn't exist naturally. It's created by humans. Must be naturally occurring. Number 3, the substance must be inorganic, meaning not coming from living or made of living things. So if you talk about, tree branches or leaves, they cannot be considered minerals because they are organic. That is, they came from living organisms. Another example would be coral. Coral is made by small sea creatures, and therefore it's organic material and cannot be considered a mineral. Minerals must be inorganic. Number 4, the substance must have a fixed chemical formula, meaning it's made up of a specific combination of elements. Let me give you an example. The mineral quartz is composed of silicon and oxygen bonded together, specifically 1 silicon bonded to 2 oxygen atoms. All quartz is made of this chemical formula. Another example, pyrite, often known as fool's gold, has a chemical formula of Fe, which is iron, and S, which is sulfur. And when these are bonded together in this particular arrangement, you get pyrite. So criteria 4 is that the substance must have a specific or fixed chemical formula. It has to be made of a specific recipe, if you will, of elements. And then finally, criteria number 5. The atoms that make up the substance must be arranged in an orderly crystal structure, a specific structure. Let me give you an example of this. The majority of the minerals that exist on Earth's surface are considered silicates, and that means they're made up of, in part, silicon and oxygen. The silica tetrahedra is the most common arrangement of silicon and oxygen atoms within a mineral. It looks something like this model here, where the red balls of clay represent oxygen atoms and the gray is a silicon atom. And you can see they're bound together in this tetrahedra shape, and this becomes the most common building block of minerals on Earth. So that's what we mean when we say the atoms must be made up of a specific orderly structure. I'll give you another example of that in just a minute. So let's test ourselves a little bit. Here are those 5 criteria. Must be solid, naturally occurring, inorganic, have a fixed chemical formula, and a specific atomic arrangement. So, what about this pool of liquid mercury? Can this be considered a mineral? Well, if you look at criteria number 1, it says it must be a solid, and this clearly is a liquid, so sorry mercury, you're not a mineral. What about this chunk of bituminous coal? Well, if you know anything about coal, you would know that it's actually formed from ancient tropical plants that have been compressed and squeezed together for millions of years. So it is a solid, and it's certainly naturally occurring, but because it's made from plants, it is organic, and therefore it doesn't meet criteria number 3. And so coal is not considered a mineral. Well, what about ice? This is an interesting one. Let's go through our criteria. Is ice solid? Yes. And it does exist as a solid on at least some parts of the Earth, the poles specifically, and high up in mountains, you get water that exists naturally as a solid. So that's fine. Is it naturally occurring? Of course. There's quite a bit of ice naturally existing on Earth. It is not an organic material. It is not living. It never was living, and is not made by living things. It does have a fixed chemical formula, H2O, and it does have a specific atomic arrangement. So is it a mineral? Well, according to our criteria, yes, it is. However, there's a lot of debate about this, and some people think ice should not be considered it because most places on Earth it would exist as a liquid. So we'll give that one a question mark. What about this substance? This is sulfur. As you can see, sulfur exists as a solid. That's good. It's naturally occurring. It forms along volcanoes. It is inorganic. It's not living, and it never was living. It has a specific chemical formula. It's composed of the element sulfur. And it has a very specific atomic arrangement. If we could zoom in, we would see the atoms arranged in a specific way. So, for our criteria to be met, sulfur works. So, it is considered a mineral. Now, let's move on. I want you to keep in mind that all of the physical properties of a mineral, and what I mean by that is the colors, the shapes, the textures, the smells and the tastes, the appearance, the hardness, the sheen, all of these physical characteristics of minerals result from one specific thing, and that is the internal arrangement of the atoms. To give you an example, that sulfur we were just looking at is yellow. The reason it appears yellow is because of how these sulfur atoms are arranged inside. Quartz sometimes appear clear, and that's because of how the atoms are arranged. The mineral halite tastes salty because of how the atoms are arranged. The mineral sulfur, again, has kind of a rotten egg smell, and that's a result of the internal arrangement of atoms. So all of the physical properties result from how those atoms are arranged. Let me give you one really neat example of this. This is a diamond, the hardest mineral that exists on Earth. Fairly rare in nice, complete crystals. It is the hardest substance. It has a hardness of 10 on something called the Mohs hardness scale, which we will learn about. Now, diamond is composed of one element, and that is carbon. If you could zoom down inside this diamond, you would see the carbon atoms arranged in a pattern like this. Notice how all the atoms are interlocking, connected to one another. This creates a really strong bond which is what makes diamond such a hard mineral. But let's look at a different mineral. Did you ever wonder what made a pencil write? A lot of people have the misconception that it's lead. It's actually not lead. It's a mineral known as graphite. Interestingly enough, graphite, like diamond, is made up of only carbon. But if you look at how the carbon atoms are arranged, they're arranged into these sheets, which are not very well connected. The result is that though it's made of the same elements as diamond, it's a much, much softer, weaker mineral. So again, what gives these minerals their physical characteristics is how the atoms are arranged inside. So let's do a quick recap. First thing we talked about was how minerals are the building blocks of rocks, how they have lots and lots of uses on Earth. To be considered a mineral, it must meet our 5 criteria. It must be a solid, it must be naturally occurring, it must be inorganic, it must have a specific composition, and finally, it must have a definite structure. Thanks for listening.
Okay, so let's talk about what the 5 requirements are for minerals. Number 1, it's naturally occurring. Number 2, it's inorganic. Number 3, it's a solid. Number 4, it has a defined chemical composition. And number 5, it has an ordered internal structure. So let's look at what each of those mean. The first, naturally occurring. It's formed in nature, not formed in factories. So we have some minerals that are formed in labs, like the lab-grown diamond versus a natural diamond. And this is the way that we're able to synthetically create minerals. But when we talk about minerals, we say that they're formed in nature, that they're naturally occurring. They're inorganic. Okay, so organic chemicals consist of molecules that include carbon and either form in living organisms or have structures similar to those in living organisms. Almost all minerals are inorganic. So is it alive? And the answer is no, so it's inorganic. And what qualifies as almost? So some geologic formations have been formed from bat guano, which is really interesting. There's a podcast I listened to about farming or like mining some solidified bat guano and how that's used for fertilizer. So this is one of those almost and in the gray area of definition. But when we think about organic, organic means it's living, and minerals are not living. It's solid. So a solid is a state of matter that can maintain its shape indefinitely and thus will not conform to the shape of its container. And things that do conform to the shape of their container include liquids and gases, and those are not minerals, so it has to be solid. It has a definable chemical composition. There is a chemical formula for a mineral. Some minerals contain only one element, but most are compounds of 2 or more elements. For example, quartz is silica and oxygen, SiO2. But then we have another mineral, biotite, which is a bit more complicated. It has iron, magnesium, potassium, aluminum, silica, oxygen, and hydrogen. So it has a definable chemical composition, but it's a little bit more intricate than some others. It has an ordered internal structure. So atoms are fixed in a specific orderly pattern. The pattern itself is often referred to as its crystal lattice. And the YouTube video alluded to this when we talk about the differences between diamond and graphite, even though they're the same, they have the same chemical composition, they have a different internal structure. And diamonds have a much tighter structure, and that's why the mineral itself is much harder. So the internal structure is one of those characteristics of the mineral, and it helps us identify the mineral, which we'll talk about here in a second. Okay, so the video talked about ice. So what do you think for a snowflake? Do you think a snowflake is a mineral? Well, technically, it's in that gray area, but technically, yes, it's considered a mineral. Snowflakes are made of ice, and it is naturally occurring, and it is solid. It's inorganic. It has a definable composition, H2O, and it has an orderly arrangement of atoms. So yes, it's considered a mineral. The video did say, though, that this is a gray area because not all places where there's snow or ice remain as ice. So it could be considered not solid. It would be water in that case. But for this purpose, it fits the criteria. Okay, what about glass? What do you think? So it meets quite a bit of the criteria. It's homogeneous. It's naturally occurring. Volcanoes and impact craters can produce glass. It's solid. It's inorganic. It's not alive. It has a definable chemical composition, which is silica dioxide, but it does not have an orderly arrangement of atoms. And this is why it's not truly a mineral. So even though it meets the other criteria, it doesn't meet that last one. So it is not a mineral. So how are minerals formed? Physical and chemical conditions must be favorable, and there must be sufficient time for those atoms to become arranged. Physical and chemical conditions include factors like temperature, pressure, presence of water, the pH, how acidic it is or basic, and the amount of oxygen that's available. So most of the minerals that make up the rocks around us formed through the cooling of molten rock. And so that's the majority of how rocks and minerals are made. But there's also a few others that are made through the precipitation from aqueous solution. There's precipitation from gaseous release, metamorphism, weathering, and even just organic formations like shells and bones for calcite. So some of these other ways of how they're formed, we're going to talk about throughout this semester. But most of the minerals are formed through cooling of molten rock. So how can we tell one mineral from another? These are some of the characteristics that we use. First is color, streak, luster, hardness, specific gravity, crystal habit, fracture and cleavage, and any of the other special properties that may be associated with the mineral. So let's talk about each of those individually. Well, color seems somewhat intuitive. Color is just the way that the mineral interacts with light and how our eyes absorb that light. So the mineral absorbs certain wavelengths and reflects others. So the color you see when you're looking at a specimen represents the wavelength that mineral reflects and does not absorb. So we have an example here on the right. This is quartz. And quartz can come in different colors. And so we use these other adjectives to describe the specific color of quartz. So they're all quartz, but we have milky quartz, which has a whitish color, and we have rose quartz, which has a pinkish color. Okay, streak refers to the color of a powder that's produced from the mineral. So if you were to use a scratch plate, which is like a porcelain plate or a ceramic plate, and you were to scratch the mineral on top of that plate, sometimes it leaves this streak. And this streak may have a slightly different color than the rock itself. And this can be informative of trying to figure out what type of mineral it is. For example, on the left, the sample there is really dark looking, but kind of shiny. And then the streak actually has a little bit of brownish color to it. This is not uncommon with some minerals that have a different streak than the main color that you see of the rock itself. Okay, luster. So when a light beam hits a mineral surface, some of it undergoes scattering. So luster refers to the way that the mineral surface scatters light. And there's a few words that we use to describe luster when we're looking at different minerals, and try to think of what that would feel like or what that would look like. So when we use for non-metallic minerals the word silky, that's definitely like a texture that you might be able to feel. It would be smooth, right? Or glassy, that's completely different than what silky would feel like. Or satin, or pearly, earthy. Some other kinds of luster could be, so we have non-metallic and metallic. So some of those words that I just described would be the non-metallic. But for metallic luster, it could be, a very shiny, or it could be brilliant. Some of these other words that might describe the type of luster. The hardness scale. So over on the right-hand side is a way that we're able to basically lump and split different minerals based on how hard they are relative to common objects. So this is the mineral's ability to resist scratching. And so if you were to identify minerals, you would start with the lowest common object here. So if you were to start identifying minerals, you would start with your fingernail. So you would have a mineral sample and you'd scratch it with your fingernail. And if you could see a mark on the mineral from your fingernail, then you know that the hardness of that sample is less than the fingernail. And so you can go up in hardness. For example, like a steel nail is considered a 6.5 on this scale. And so this is a way to try to figure out how hard the mineral is. And if you were to scratch the rock or the mineral and you can see the scratch, that means the mineral is not as hard as that common object. Okay, specific gravity, or also known as density. So this represents the density of the mineral, and it's the ratio between the weight of a volume of mineral and the weight of an equal volume of water. So for example, a piece of galena feels heavier than a similar piece of quartz. So just think about this as how dense it is. How heavy does it actually feel for the size of sample that you would have in front of you? Crystal habit. So the shape of a single crystal with well-formed crystal faces, or the character of an aggregate of many well-formed crystals that group together as a group. So an example of this is asbestos, which is very fibrous. But if you were to look at it at high magnification, this looks like a bunch of tiny needles. And so this is the shape of a single crystal. And we use these types of, whether it's the mineral itself in like a large sample, or if you look at it under a microscope, these are some of the things that we can describe what the crystal habit is. Okay, next is fracture or cleavage. So minerals can fracture or break in different ways depending on the internal arrangement of those atoms. So if a mineral breaks to form distinct planar surfaces that have a specific orientation to the crystal structure, it has cleavage. And the surface is a cleavage plane. So think about maybe a loaf of bread. So you have a loaf of bread and you slice the loaf of bread. Those slices represent the specific orientation of the crystal structure. So it's being sliced in one direction. And it has cleavage at that surface. So between the slices is considered a cleavage plane. That's somewhat similar to this zoomed in picture of mica in the top right-hand picture. And if you see the zoomed in view, you see all these little sheets, and that's a distinct cleavage of mica. And the difference of those sheets versus the picture below is that halite breaks off into cubes. So halite has 3 sets of cleavage planes that intersect at right angles. And so these right angles create cubes within the mineral. And these are, again, other ways that we can distinguish between the two or distinguish between minerals is if they have fracture or if they have cleavage. Some other minerals have special properties that can set them apart. So calcite reacts with hydrochloric acid to produce carbon dioxide gas. And you can use hydrochloric acid to put it on top of a sample, and you can see little bubbles and gases forming. The picture on the right, magnetite, can be attracted by a magnet, and graphite makes a gray mark on paper. So that last special property is a little bit more like sort of like the streak of the mineral, but these are just some of the special properties that set certain minerals apart from each other. Okay, so let's look at a few pictures here, and let's describe what you see. Okay, so in this picture, let's think about how you would describe this mineral. Just think for a second, but I'm going to just throw some words out there of what maybe some observations you might have. It looks kind of clear, or maybe it's white. That would be a way to describe its color. We can't really use a streak plate in this case, since it's just a picture. But what do you think about the luster? Is it shiny? Is it dull? To me, it looks a little bit dull. It looks pretty hard, but again, it's hard to tell without looking at the sample. It does look pretty dense, and you don't know too much about the crystal habit, but we can see that it does have some fractures because it's in kind of like this cubic rectangular shape. So if we were to just throw some words out there, I would say it has kind of a rectangular shape. It is dull, it's clear or white. Okay, what about this one? Quite a bit different, right? This looks yellow to me, and it doesn't really look all that shiny. It looks kind of puffy. I don't know, let's see, what would puffy? Puffy might go under density. It's hard to see anything else about the crystal habit or whether it has fractures or cleavage, but in this case, I would say it doesn't really look like it has any fracture or cleavage, so that would be a fair observation just to say none, no fractures. What about this? This looks kind of brown or gray. Again, can't really tell too much about the streak, but it's kind of shiny. It's platy. Do you see how it has like these sheets? So maybe I'll put sheets down. Plates might be another one. It looks light. It also looks really delicate. So these are some words that come to mind when I look at this sample. Okay, one more. And this looks like gold. Do you see like the little cubes in there? That would go under, we have cubic here, that would go under fracture or cleavage. This looks really heavy. It looks really dense. It also looks like it is really robust. It would be very hard. It's metallic. So maybe that would be part of streak as well. Okay, last one. This looks white. This looks kind of dull or maybe even soapy. It has like a kind of this kind of a shine, but not quite shiny. It has what I would call maybe a soapy luster to it. There's some streakiness in there too. It's not all white. It has maybe some yellow or brown colors in there as well. So these are just some thoughts that come to mind of when you're identifying minerals, of how easy it is to make some initial observations. And then all you have to do is just put them into these different categories of what you're able to observe just from a picture without even holding the sample in front of you. Okay, so when we talk about mineral classification, these are how we lump and split minerals. We lump and split them into silicates, sulfides, oxides, halides, carbonates, metals, and sulfates. So silicates are the fundamental component, and most silicates in the Earth's crust is silicon and SiO4. So silicates make up a majority of the Earth's crust. Sulfides consist of metal cation bonded to a sulfide anion, like pyrite. Actually, one of the pictures I just showed you was an example of pyrite. Oxides consist of metal cations bonded to oxygen anions, such as hematite or magnetite. Halides are anion, and a halide is a halogen ion. So some examples of those are halite or fluorite. Carbonate minerals or carbonates are minerals in which elements like calcium or magnesium are bonded to. So those examples would be like calcite or dolomite. Native metals, like pure masses of a single metal, like copper or gold. And sulfates are metal cation bonded to the silicates anionic group. Many sulfates form from precipitation out of water near the Earth's surface. An example of that would be gypsum. So like I said, silicates are the major rock forming mineral at the crust, and silicates make up over 95% of the continental crust and almost 100% of the oceanic crust. Silicates are the most common mineral. So and it's SiO4, so 4 oxygen atoms surrounded by a single silicon atom. And there are different arrangements of the oxygens and silicon. So these could be tetrahedra, these could be single chain, double chain, sheets, and framework silicates. So these are all different types of silicates that can be formed with the same chemical composition. So one last category we didn't really talk about are gems. Gemstones are particularly rare and beautiful minerals. So these gems are technically minerals, and their jewels found in jewelry have been faceted. They've been carved and they've been cleaned. So some of the faces that you see on gems are not actually like cleavage surfaces. Those could just be like man-manufactured. So the fire of a jewel comes from the way it reflects light internally. Okay, so what did we learn today? We learned that minerals are naturally occurring solid substances. They are formed by geologic processes. They have a definable chemical composition and an internal structure characterized by an orderly arrangement of atoms, ions, or molecules in a crystalline lattice. Most minerals, I'd say all minerals, are inorganic. Minerals can be identified and classified based on those physical properties like color, streak, luster, hardness, density or specific gravity, crystal habit, cleavage, anything special that would be unique to that, like magnetism or reaction with acid. Minerals can be grouped into different classes like silicates, oxides, sulfides, sulfates, halides, carbonates, and metals. And silicate minerals are the most common minerals on Earth. And that's it. See you next time.